All right, so far we've been able to figure out the enthalpy of stream 3 for the irreversible case, for a compressor that does have an efficiency of 75%. We still haven't figured out, you know, the work required for the compressor or the mass flow rate. And so what we're going to do is we're going to continue on through the problem. And so the next step we're going to continue to is going to be the condenser here. Okay. All right, and so we're going to deal with the condenser now. So that means we're going to go from stream 3 to stream 4. All right. So for the material balance, it's just going to say that stream 3 is equal to stream 4 is just equal to that same mass flow rate we were dealing with before. For the energy balance, we have the open system energy balance. So the heat here is going to be QC. So it's this one here. And then we have the enthalpies of things going into the condenser and things coming out of the condenser. Okay. All right. So left-hand side, still steady state. Don't have to worry about it. No shaft work. Okay. All right. And these mass flow rates are the same. So what we get, once again, is, a case where we could take the QC and divide it by the mass flow rate to get a statement that looks like this. Okay? Oh, whoops. That should be the other way. H4 minus H3. Okay? All right, and so for H4, this is something that we could get from the thermodynamics plot. So here, stream 4, we know it's a saturated liquid at 25 degrees Celsius. We found that intersection. So all we have to do is kind of go straight down. Okay? And here we see that enthalpy for H4 is basically about 230 kilojoules per kilogram. Okay? So that's something we know. And then for H3 here, we already figured out what it is. Specifically, we know what it is after accounting for the efficiency of the compressor. So we have both of these values now. And so if we add them together, or find the difference, it's going to be this. Okay? All right, so we were able to figure out QC over this mass flow rate. All right? And so let's take an account of everything we know so far. So what we know are QH. Remember, this was that 100 kilojoules per minute, so something that was from the problem statement. And we know WC over the mass flow rate and QC over the mass flow rate. We got this from our energy balances. What we don't know right now is the mass flow rate, okay? Or kind of equivalently, we don't know QH over the mass flow rate. So what we could do in order to figure out this is we could solve for it by doing an overall energy balance over the entire cycle. Okay? And so what I mean by that is rather than just doing energy balances on the individual units, what we could do is we could do an energy balance around the entire thing. And if we do that, what we see here is we have heat going in and also some sort of work, and then QC coming out. And there's no mass crossing the system boundaries. Okay? All right, and so with that in mind, we could set up an overall energy balance. Right? So once again, this refrigeration cycle operates in a cycle. So the left-hand side is going to be 0. And because we're doing the entire system, right, there's no mass that crosses our system boundary anymore. So this is going to be 0. Okay? And so what we have now is left-hand side is 0. And on the right-hand side, we're going to have QH plus QC plus WC. And we want the real WC, the one that's irreversible. Okay? So this is what our energy balance statement says. What I'm going to do now is I'm going to divide the entire equation by the mass flow rate. And that's fine to do because on the left-hand side it's just 0. Okay? And I'm going to rearrange this such that on the left-hand side I'm just going to have QH divided by M by itself. And the right-hand side, I'm going to have this. Okay? And the reason I set it up like that is because here we have QC over M, which is what we solved for earlier. And then we also have WC, irreversible over M, which is what we solved for back here. So we know those two values, so we could just calculate this. And when we plug in for that, we have 175 kilojoules per kilogram. Right, so that's what this sum equals to. And here, we know what QH is. So that's 100 kilojoules per minute. What we don't know is m dot. All right, but at this point, that's our only unknown. And so we could solve for it. And so from this overall energy balance, we actually get the mass flow rate, which is going to be equal to 0.571 kilograms per minute. And now that we have the mass flow rate, we could actually just go out and solve for WC irreversible. So that's going to be the mass flow rate .571 times that 26.7 kJ kg. Okay? And we get that the work required for the compressor is this. Okay, all right. And so, by kind of going through the balances, we figured out the mass flow rate and the work needed for the compressor. But there's one last thing we need to figure out, which is the coefficient of performance. Okay? Or the problem statement didn't ask us to calculate it, but for refrigerators, this is a sort of parameter that you calculate because it tells you how good your refrigerator is working. Okay? And for the coefficient of performance, it's essentially a ratio of what you want. So in our case for the refrigerator, we want to keep QH as large as possible because that means you're removing as much heat from the contents in your refrigerator as possible. And you want to divide it by the work or the power needed for the compressor. Right? So specifically the compressor that's inefficient. All right, and so we know that QH is going to be 100 kJ per minute. And this is going to be 15.2 kJ per minute. If you take that ratio, it's going to be about 6.58, or 6.58. And so, with a coefficient of performance, essentially the larger this number is, this means the better your refrigerator is operating.